Hello everyone, my name is Xinhao Yuan. In this video, I'll talk about our work of effective concurrency testing for distributed systems. This work is a collaboration with my advisor Junfeng during my PhD in Columbia University, and it has nothing to do with my current employment at Google. Nowadays, distributed systems have been widely deployed all around the world and enable global scale applications. Some of the famous distributed systems have been deployed over tens of thousands of machines, storing and processing petabytes of data. With such tremendous scale of deployment, concurrency becomes a crucial part of it, and this is because the system is running on a massive number of parallel nodes, communicating with unreliable network, and handling a large number of independent client requests. Moreover, distributed systems must tolerate partial failures at any moment without bringing the system down. With all these factors, the interleaving of system operations can be very complex and hard to reason about. When unexpected interleaving shows up, it may lead the system to undefined state and further cause serious damage. To give you a concrete idea, here is an example of the real-world error that we have found in our work. I'll use the example throughout the video. The example demonstrates a scenario of the system programmed in the actor model, where the abstract processes are running in distributed nodes and communicating many through messages. One key function of the system is to maintain consistent membership in each node, so that client requests can be properly forwarded and replicated among the nodes of the cluster. To do that, each node of the system has a dedicated auxiliary process that detects any offline nodes and sends failure report back to the main process. The graph on the right shows one of the normal cases of the system, where all the nodes are alive and the auxiliary process sends no failure report. The main processes of the two nodes communicate in the handshaking protocol to agree on the same membership. Besides happy cases, the system also handles failure cases where part of the cluster is down. When the auxiliary process of the A detects that node B is down, it will send back the failure report, so that the main process of A will wait for B to come back. Later, when node B comes back, it will initiate the same handshaking process so that A and B will recover to the same membership again. So far, everything looks good. Although the system tries to handle all possible situations, it didn't expect that the failure report could arrive later than the actual node coming back and finishing the handshaking. When such interleaving occurs right before the failure report, two nodes will still agree on the same membership. The delayed report will make node A believe that node B has disconnected after the handshaking, and A will remove B from its membership and wait for B to initiate the handshake again. However, B still believes that it is connected with A, and thus it will not restart the handshaking. At this point, the system will not recover from the split view of the membership and will refuse to handle any client request, ultimately causing unavailability of the service. To detect such unexpected interleaving before it causes damages in production, concurrency testing takes such scenarios and repeatedly explores their possible interleavings. One classic approach here is systematic testing, or model checking in some context. It exhaustively enumerates all the possible interleavings of the test scenarios to surface any corner cases. Unfortunately, one inherent problem of systematic testing is the scalability, as the number of possible interleavings grows exponentially to the size of the scenario, which leads to the astronomical number of interleavings to explore even for small and simple multi-threading programs. Such problem is often called state space explosion. And other than systematic testing, randomized testing randomly schedules the operation in test to sample their interleavings, which is simpler and more lightweight than systematic testing. Among randomized testing approaches, probabilistic concurrency testing, or PCT for short, leverages the observation that real-world concurrency errors usually have a small set of root cause operations interleaved in an unexpected way. To quickly find such errors, PCT explores the test by randomly choosing a small subset of operations to interleave despite other operations. Studies have shown that it can effectively find real-world errors in simple test scenarios. However, PCT still suffers from the complexity of the test, since first of all, it must choose the right subset of operations that covers the root cause of any error. Unfortunately, due to the complexity of the real-world distributed systems, even the simple test of the concurrency error can have an order of magnitude more operations than previously studied tests. Thus, PCT only have negligible probability to surface the error. For example, the real version of the scenario I used before has more than 6,000 operations to explore. The complexity of testing distributed systems comes from two aspects, which I will still use the example to demonstrate. First, although the test scenario so far only shows the root cause of the error, to enable such root cause, the test has to include more dependent operations that bring up the system with the distributed setup. And the system also depends on low-level runtimes to properly initialize. For some of the concurrency errors we've studied in distributed database, the scenario depends on setting up tables replicated in multiple nodes, which are further more complicated than the scenario I showed here. Moreover, concurrency errors in distributed systems are often high-level, which do not directly expose low-level symptoms, such as crashes and deadlocks. Thus, to detect them, tests usually come with extra operations that validate the system state. For the example scenario here, it sends client request and checks its response. And when the error is triggered, the client request will get stuck and the error is exposed as a deadlock. Another source of the test complexity comes from the expansion that each high-level operation is implemented with multiple low-level primitives. In this example, under the hood, the accelerate process is the RPC service, which takes request messages from the main process, and the liveness detection of the nodes are implemented by looking up the registry of the nodes for the process symbol. Since concurrent testing explores the interleaving of low-level primitives, such expansion of details further complicates the test scenarios, including the root cause of the errors. To tackle the complexity of testing distributed systems, we introduce Morpheus. For a quick overview, Morpheus is an in-situ concurrency testing tool for unmodified Erlang distributed systems. We leverage two techniques to handle the complexity of testing. The first is partial order sampling, or POS for short, a randomized concurrency testing algorithm from our previous work. It has very nice properties of manifesting simple root causes despite extra dependent operations. The second technique we introduced is conflict analysis, which continuously analyzes the explored executions and identifies critical operations that may affect the testing result. And Morpheus can focus on exploring the interleavings of the critical operations instead of the operations. With the two techniques, Morpheus found 11 new concurrency errors in 4 distributed systems, and our evaluation results showed that it outperformed other concurrency testing approaches. Now I'm going to further explain the key techniques. Partial order sampling was originally designed for uniformly sample partial orders of interleavings in a test scenario. The algorithm is extremely simple with 2 steps. First, given a test scenario, every operation of the test will be assigned to a uniform random priority from 0 to 1. Then when the algorithm schedules the test, it always selects the available operation with the highest priority. Compared to PCT, POS eliminates the small budget for interleaving operations, while it can still effectively interleave the small root causes of the error, even with the presence of the extra dependencies. And this is because in POS, there are always local sufficient conditions to interleave any subset of operations whose ordering is not affected by other operations. Thus, POS can independently decide the ordering by comparing their priorities. For example, no matter how many operations are preceding or following the 3 operations here, POS can always enforce their interleaving by having the priority in the showed ordering. And the same properties also apply to the example arrow. If we annotate the priority of each operation of the root cause with a variable, the the local condition of the priority is shown here, which is simple and easy to satisfy. Although POS resolves the problem of dependent operations, the low-level details can still make the root cause larger and thus lower the guarantees of POS. To further reduce the size of root causes, we leverage the insight from systematic testing and distinguish operations into conflicting and non-conflicting operations. Conflicting operations are those operations which may be concurrent with other operations accessing the same resources, such as sending messages to the same process. By semantics of concurrent programs, only reordering conflicting operations can affect the execution result. Thus, to produce any testing result, it is enough to interleave only conflicting operations while scheduling non-conflicting operations as soon as possible, effectively ignoring them during the exploration. Such as here, the spawning of the auxiliary process as well as the monitor request message never conflict with others, and we can always schedule them right after the previous process registering operation. The intuition is simple. However, the challenge here is to identify conflicting operations during the randomized exploration. Since there is no way to know if an operation is conflicting in a randomized test until the execution ends. Morpheus instead continuously analyzes the exploit execution of the test, keeps track of any conflicting operations discovered so far, and only explores the interleaving of discovered operation in POS while immediately scheduling others. Such process is incremental. Initially, no operation is discovered. After each exploration, Morpheus analyzes execution to add any conflicting operation in this execution to an accumulated table. After more and more exploration, the discovered operation will converge. It can be proved that any conflicting operations will eventually be discovered given enough exploration, and operations that never conflict will not be included. And with the reduced number of operations to explore, POS can have a further better guarantee to find errors. We evaluated our approach compared to other concurrency testing approaches. For brevity, I will only show the comparison of Morpheus to the other randomized testing approaches. And please read our paper for more detailed evaluation, as well as the study of errors we have found in this work. The graph here compares the error finding performance of different approaches. Each group of bars shows the ratio of test runs that manifested the error, divided by the total number of runs. And each color represents a randomized testing approach. Note that here we also compare the improvement of conflict analysis over POS by showing the data of POS alone next to the Morpheus. Finally, each group of bars are normalized by the best ratio annotated under the name of each arrow. From the graph, with POS and conflict analysis, Morpheus performed the best for the majority of the error we studied. The result of average data further shows that Morpheus outperformed PCT and random work with more than 180% advantage, and conflict analysis improved the performance of POS by more than 60%, which demonstrates the effectiveness of our approach. To conclude, concurrency in distributed systems is inherently challenging due to high complexity of design and the large scale of deployment, which further makes the testing hard for even simple errors. To address the complexity, we proposed Morpheus, which uses the combination of partial order sampling and the conflict analysis to find real-world errors in complicated distributed systems. Evaluation results showed that our approach outperformed the existing concurrency testing approaches. And that's all for the video. Please read our paper for more details and feel free to contact us for any questions. Thank you.